In this video, we're going to talk about a football that's kicked into the air, and we know the football's location at 3 different points. And using just algebra, quadratics, and functions of x, we are going to be able to figure out the entire trajectory of the ball and predict everything about the ball's motion and path. So that's what's in store for you today on High Peak Education. What's going on, everybody? It's Paul Culette here coming at you with a new video, and this is going to be the last video of 2020. And I hope you all have had a safe and productive year despite all the challenges that there have been worldwide. But this video is a really interesting application of quadratic functions and parabolas and algebra, and even things that you may know and love, like the quadratic formula. One of the things we're going to see is we're going to see why, by the end of this video, that we need to have the football's location at 3 points in order to generate this quadratic function, which is when a football is punted, it goes up into the air and reaches a maximum altitude and comes back down. When the ball is kicked, it was 4 feet above the ground. 1 second later, it was 28 feet above the ground. 2 seconds after it was kicked, the football was 28 feet up. Okay, what are the variables in this situation? X for the independent, Y for the dependent. B, make a table of the values given in the problem and then sketch a graph. Don't forget to label the axes and show a scale. C, use your graphing calculator to write an equation for this situation. D, write the coordinates of the vertex, explain its meaning. E, how long is the football above 20 feet? F, when will the ball hit the ground? G is domain and range. Okay, domain and range of this function. Okay, first of all, let's just kind of reread this and then we'll start tackling each section one by one. When a football is punted, it goes up into the air, reaches a maximum altitude, and comes back down. So basically what we're saying is that conceptually it looks something like this. That if they've got some vertical axis and some horizontal axis, y and x, then like the ball looks kind of like this, right? So we're saying it's going to go something like this, from here to here. Now, by the way, do you notice that it's kind of a parabola, but it doesn't necessarily start at 0 for y, because it starts at 4 feet above the ground.
Right.
So we're thinking that this right here is 4 feet. Okay?
Okay.
Now, it also says that when the ball was kicked, it was 4 feet above the ground. So this point right here is at 0 seconds, right? It says 1 second later, it was 28 feet above the ground. So maybe like this right here this is 0 seconds, but say right here, this is 1 second, and 1 second, it's 28 feet above the ground, right? So that's right here, and this is in feet. And then 2 seconds later, after it was kicked, the ball was 20 feet up.
Okay.
Now, by the way, do you notice that it's 28 feet above the ground here, but maybe it's like already right here, that it's 20 feet above the ground, so that's at 2 seconds. I mean, this is all a sketch, but you're getting the idea, right? 28 feet is the location of 1 second, but then 20 feet is the location of 2 seconds.
Right.
So this is like, say, 20 feet, whereas this is 28 feet. So we don't even exactly know how this is looks, but we're trying to get some handle on it. Okay?
Right.
Now, by the way, we want the variables in this situation. Now, they don't give us any information about how far it goes this way. So how far horizontally, that is not known. We don't know if this ball goes more or less straight up or if it goes very horizontally. We just know what? We know the number of seconds, so that's information about the what variable. Right, and that's going to be, is x going to be horizontal distance, or is x going to be, what's the t word I'm thinking about?
Time.
Time. So wouldn't this be the independent variable?
Yes.
Because we're just going to choose either 0 seconds, 1 second, 2 seconds, and so on.
Right.
All right, then we want the dependent variable.
Okay.
So the dependent variable is what? What's on the y-axis? What are we sort of plotting, if you will? Distance in which direction, though?
Vertically.
Vertical, right. So it's the vertical distance. And by the way, it's technically like the vertical distance from the ground, right? Like above the ground, right? It's not just any vertical distance, specifically above the ground. I mean, if we were doing this at Denver Mile High Stadium, we're way above sea level. Like, we're defining 0 as like the field, like the ground. Okay, B, make a table of values given the problem and then sketch a graph. Don't forget to label the axes and show a scale. Okay, so let's do x and y. So I think when x is 0, we have 4 for y. When x is 1, what do we have? What does the problem say?
Feet.
Right, this is 28. And then finally, when x is 2, this is the other piece of information we had. Y is what?
Sorry, y is 20.
20. Good job. Okay, so there we have this table of values. Let's have this be the y-axis, and let's have this be the x-axis. Now we know that certainly the ball goes up to at least 28 feet, but probably even a little higher. Because think about this, right? It goes up to 28 feet. That's not necessarily the highest height, but it's coming down. Like, why is it coming down? Because at 2 seconds, it comes down to 20 feet. Okay?
Right.
So what I'm saying is that let's maybe have each of these tick marks be about, I don't know, 5 feet. So this is 5, 10, 15, 20, and then we're going to run out of room here quick. 5, 10, 15, 20, 25, 30, and then 35 somewhere about at the top, okay?
Okay.
This is 0, and then this is x, and this is y, and this is in feet, and then this is in seconds. We know at 0 seconds we're at 4 feet, so we start right there. So this is the point 0, 4. Then after, let's have each of these tick marks be a half a second. So let's say 1 second is right here. At 1 second, we know we're at 28 feet. So that's around here. And then we know that at 20 seconds, we know that there should be, again, and this is now at 2 seconds, should be here, right?
Right.
Now what this means is, we're going to have a parabola, and let's sketch what the parabola looks like. It's probably something like this. I'm having real trouble. Sometimes I have trouble sketching graphs with this electronic. Something like that. Okay?
Okay.
So this is the full path. Okay, this is the point 0, 4. This right here is the point, let's see, 128. And this is the point right here, 2, 20.
Okay.
Okay, so any questions about how we got that?
No.
Okay. So I assume that, in fact, by the way, we know it has to go higher than 28 feet. I think part of the reason we know that is because it's certainly going down as we get to 2 seconds and 20 feet high. But notice that if this was the highest point, 128, it would be back down here at 2 seconds to 4. Like it would be like this if this was the highest point. Does it make sense?
Yeah.
Because it'd be symmetric, but it's not that way. So since it's not symmetric to this point, then we know it has to go a little higher. Use your graphing calculator to write an equation for this situation. So what we're going to want to do is we're going to want to do a fit. Now, what do we mean by a fit? I mean, it's actually somewhat difficult to come up with this equation just sort of on our own if we don't exactly know where the vertex is, okay? But we can at least kind of get a sense of what this is. So let's write this down. It's going to be like y equals ax squared plus bx plus c. We've worked on this before, right?
Right.
This is what the equation of a quadratic looks like. For one thing, we know a should be less than 0. How do we know that? Right, since it has a maximum, so the parabola has to open down. So that's the first thing. We know a is less than 0. We also know that, let's see, the x value, the time for the vertex is negative b over 2a. That has to be between 1 and 2, right?
Right.
It has to be somewhere in that domain. Now, by the way, it's probably a lot closer to 1. At least from my graph, it looks like it's maybe 1.25 or something like that. It's hard to say. But here's another thing. We actually know when x equals 0, we can plug in 0, and we find that c is equal to 4. How did we come up with that? Yes, exactly right. Yes, very good. Because notice, if you say y of x equal to 0, you put in 0 squared. Well, it's okay. So it's a times 0 squared plus b times 0 plus c. And that has to also equal 4. So 4 has to be c.
Right.
So this is the y-intercept. What I'm trying to say is that when it asks us to use our graphing calculator, we want to fit a curve, and we want to use the values of a and b, and we just basically need to be sort of a little clever in terms of just making good guesses at a and b to then get this curve. What I'm saying is that we should plot a couple points. So we should plot, let's see, so when y is, let's see, when y is 1, we know that we should have 28. When y is 2, or sorry, when x is 2, we should have 20. And we know our parabola should look something like this. It should be something like, I'm just going to make an educated guess at it, negative x squared plus, I'm just going to call it x plus 4. Okay?
Okay.
And then I'm going to I'm going to set the table, or not set the table. I'm going to so let me set this to be 20. Let me set this to be 28. Okay. And then this to be negative x squared plus x plus 4. Okay? Now, by the way, I think I realized how we can actually solve this. Now, if you look at this table of values shows you when x is 0, 1, or 2 seconds, what the x and y values are. But I'm also thinking that we should do, the table set is here. So we can start the table at 0. Let's have it every, I don't know, half a second. So then we get a little more information from the table. Notice that there's 2 unknown variables.
Okay.
B and A, there's 2 unknowns. So let's write this down. There are 2 unknowns. There are 2 unknowns, namely A and B, right? The coefficients. But the thing is, we have 2 points. So we should be able to solve for A and B. Now, we actually had a third point, but the third point allowed us to solve for C. So let's do this. Let's do y at x equals 1. So if we do y at x equals 1, we've got a times 1 squared plus b times 1 plus 4. And that should equal 28. Because notice, that's just using a parabola, and we're just like putting in this point, right?
Right.
Now notice that gives you one equation with two unknowns, because that would give you a plus b plus 4 equals 28. Now it's not super useful yet, but we can get a plus b equals 20. Now that's one equation. Let's try the next equation. That's going to be x at 2. And notice we're going to use the same parabola, but now we're going to plug in 2. So it's a times 2 squared plus b times 2 plus 4 equals 20. Do you follow how I'm doing this?
Yes.
I'm plugging into the parabola, but we already knew what the c value was, the y-intercept. So we get, now 2 squared is 4, so I think we get 4a plus 2b plus 4 equals 20. And that's 4a plus 2b, if we subtract the 4, equals 16. But then we can even make this a little simpler, because everything's a factor of 2. Divide by 2, that's 2a plus b equals 8. Now have a look at this. We have this equation, and we have this equation. We have two equations and two unknowns. I know you and I have talked about this in a previous session. We can solve this, right? And that's good, because then we can get the values of a and b, and then we can get our parabola. So we can solve this maybe by elimination, right? So you could subtract one equation from the next. Remember we've talked about this? Okay, so if I have a plus b equals 24, and we subtract 2a plus b equals 8. If we subtract the second equation, what happens to the b's? Right, the b's cancel. So we get a minus 2a, that's negative a. And then we need 24 minus 8, which is what?
16.
16. So a is equal to 16. Or sorry, negative a is equal to 16. But then a should be a negative number, right?
Right.
So a should be negative 16. Now that's good, because we expected a to be a negative number. And then now you can go back into either of the equations. So let's go back to, let's say, a plus b equals 24. But now we know a is negative 16. So negative 16 plus b equals 24. And then what we can do is we can say, well, b, just going to add the 16 over. So b equals 40, right?
Right.
So what we're assuming then is y as a function of x is going to be negative 16 x squared plus 40x plus 4. Now that should be our function.
Okay.
Now that's good, because that means we can, first of all, we can put this here, negative 16 x squared plus 40x plus 4. Now let's go back to the graphic calculator. So now let's actually modify this. Let's do negative 16 x squared, and then this is plus 40x plus 4. Now what I'm also going to do is I'm going to set the values in the graph. So I'm going to do what's called window. Now the x min, I'm going to make negative 1. We know that the minimum x value is actually 0, but I want to see the graph really well. So the x max, now by the time it hits the ground, it's probably only going to be like 3 or 4 seconds. So let's go 4. Let's have the x scale be every half a second. Y min is 0. Let's actually make that like negative 1. Let's have the y max be a little more than 28, so let's maybe have it be 35. And then let's have the y scale be 1, x resolution, and let's have the delta x be 0.001. Okay, let's graph this.
Okay.
So those are our two constant values. And then hopefully we get our parabola. Okay. Oh, hang on. It screwed up the x max. Something went wrong. X max should be 3. Yes.
Okay.
I don't know what it did, why it did that. Okay, so there's our football. You can see it, right?
Mm-hmm.
Okay, there it goes. Now let's go ahead and just take a screenshot of this, okay? And then I'm going to take a screenshot of this, and then I'm going to go over the bit paper. What's going on is this right here is the point. Again, 1/28. Now, by the way, you can see this is a half a second. This is 1 second. This is 1.5 seconds. This is 2 seconds. At 2 seconds, we get this point right here, which is 2,20. You see that?
Mm-hmm.
And then this point right here is the point where we start, right? This is, let's see, this is 0,4. Whoops, sorry. Let's go 0,4. That's this point, right?
Right.
Now, there's technically no graph down here, right? We just allow the count, and same with down here, right? And this is where it hits the ground. So first of all, do you see where it hits the ground? Like, there's a tick mark right here, just to the right of that. This tick mark is about 2.5 seconds. So it should probably hit the ground at approximately, I don't know, 2.55 seconds, something like that, okay? But this is the right curve. Part of the reason we know this is the right curve is we see that each of those horizontal lines exactly equals where time is 1 or time is 2 seconds. Do you see that?
Yes.
Okay, and then we also see that the ball does indeed go higher. So there's the vertex, right? This is the highest point of the ball. Is this making sense?
Okay.
Okay, so anyway, we think we got the right answer in terms of how we solved for A and B. Okay, find the coordinates of the vertex. Explain its meaning. So what's the formula for finding the vertex? We've talked about this before. X of the vertex should be, I wrote it down before.
X minus H.
It is going to be HK, but I want to find just the X coordinate of the vertex from the general form.
Oh.
And how do we do that? It's a formula you see right here, which is what? Negative B over 2A. Good. And we spent that time solving for B and A, so we can get so negative 40 over 2 times negative 16, right?
Right.
Okay, so we get, let's see, that's negative 40 over negative 32. All right, so negative over negative is what sort of a number? So it's negative 40 over negative 32. So negative divided by negative is what sort of a number?
Positive.
Positive. And then we're just going to do 40 divided by 32 and put that in lowest terms. So you get 1.25, but let's get that as a fraction. So that's 1.25 seconds, which is the same thing as 5/4 of a second. Okay?
Mm-hmm.
Now, we also need to find the maximum value. Now, this is where we can certainly plug it in, but you can also talk to the calculator. Remember we did that thing on the table? We can do table set. We can start the table at 0, and then now we can do delta table is 0.25 every quarter of a second. Now, if we go over here to the table, we can just say, hey, table, what is the value of y there? Well, the value of y there should be 29. Do you see that?
Yeah.
29. And notice that's a little bit higher than 28. And it's certainly higher than 20. But that's the value that it gives us. And I guarantee if we plug in 5/4 of a second to negative 16x squared plus 40x plus 4, I guarantee you get 29. I mean, you got to work it all out, but you just get 29. Okay? So, might as well use the calculator if you've already got the data in there. You know what I'm saying? I mean, there's no need to go through a lot more math effort. So, again, y at x equals 1.25 should equal 29. So the vertex is going to be 1.25 comma 29. All right, so that takes care of that. And then we need to interpret its meaning. So the vertex, here's the vertex, right there. Vertex So if that's the vertex, that's what property does the ball have at the vertex? It's at its highest what?
Maximum.
Right, so it's at its highest point. So what we could say is we could say here, explain its meaning. The time and height of the ball's maximum, the time, let's just say time and corresponding maximum height of the ball. Okay, I know it's going over some, let me just make this a little smaller. Okay, so you should be able to see it there, right?
Yeah.
Time and corresponding maximum height of the ball. Okay, awesome. For how long is the football above 20? Well, let's see. We know that it's at 20 feet at 2 seconds. Do you agree with that?
Yes.
We see that here. We can also see that this right here would be 20 feet. If we skip, this was our sketch. So this up here was our sketch. And then we also see here, this is the 20 feet line, right? This is the 20-foot line. This is the 28-foot,
Right.
correct? Okay. So what I'm trying to say is that how long is this period of time between when the ball's at 28 feet and when the ball's at 20 feet? How many seconds? Not 2. We go from, yeah, this is 1 second. So listen to me. I think all we really need is we really need to find this. We need to find this time and then just add them together. Do you see that?
Yes.
So we need to think about this point, because this point is where the ball is at 20 feet. Okay, so what we want is we want to do this. We want to say, find the earlier x. So we're going to find the earlier value of x, where, let's see, y of x is equal to 20, which again is equal to our function, negative 16 x squared plus 40 x plus 4.
Right.
So I'm going to find the earlier x. Now, in order to do that, we need to solve, okay? So we need to get 0 on one side, right? So we need to subtract what from both sides? Yeah, exactly. Subtract the 20. Very good. So this would be minus 16 equals 0, right? Okay. Now, by the way, before we do the quadratic formula or try to factor this, I'm going to recommend that we divide the entire equation by negatives, just because the front term and the back term will both become 1, which will just make the quadratic formula. Now, I know this will be a fraction, but it won't be too bad of a fraction. So this will be x squared. This will be plus 1. But then we need to work out what 40 over negative 16 is. So let's see, I think that's 10 over negative 4, which is negative 5 over 2. And there's going to be an x there, right?
Right.
So this is not too bad. It's x squared minus 5 over 2x plus 1 equals 0. Okay? I think we can solve that, right? All right. Now, by the way, we know that one of the terms should already be 2. So watch this. Watch how clever we can be. We can go x and x equals 0. We know that it should be minus minus because, well, I mean, the last term's a plus. And then, here's what we need to say to ourselves. We need 2 factors of positive 1 that add up to negative 5 over 2. Now listen to me. One of them we know will be 2. Why is that? Because if you look back here, we know that at 20, for the height, one of the times must be 2. Do you agree with that?
Mm-hmm.
It must be. So that's why we get a 2 there. 2 times some number equals, negative, let me get this right. Negative 2 times some number. There we go. And by the way, the number is negative, n is less than 0, gives 1. But then negative 2 plus that number gives negative 5 over 2, right? So that's
Right.
the whole last term versus middle term. So we should be able to solve for n without too much difficulty here. So we've got to divide by negative 2. So n should be negative 1 over 2. And if we plug that in, we should hopefully be able to confirm, because negative 2 is the same thing as negative 4 over 2, plus negative 1/2, which is the n value, should equal negative 5 over 2, right? And that's correct. So this right here is 1/2, like that. Do you see that? Okay. So given that this is 1/2, then yeah, basically you just get x equals 1/2 and x equals 2. Now, by the way, that 1/2 works out really beautifully, because here is 0.5. So if you go right above here, you can see that's exactly this point, right? From 0.5 to 1, that's 1/2, but then from 1 to 2 is 1 second. So when we go to answer the question, how long is the football above 20 feet? Well, it's half a second plus 1 second, and that's 1.5 seconds, right?
Right.
So that's our answer. Okay, letter
Okay.
F. When will the ball hit the ground? Okay, so what's the y value when this hits the ground? Yeah, 0. Y equals 0, and that's going to be negative 16x squared plus 40x plus 4, right?
Right.
Okay, so now we can solve this. Now, by the way, what's the first rule of all factoring is to factor out the greatest what? Yes, good. We've talked about this before. Greatest common factor, which I think all of these terms have a 4 in it, right?
Mm-hmm.
So let's do that. Plus 10x plus 1 equals 0. And if you divide 0 by 4, nobody's feelings gets hurt. So it's just negative 4x squared plus 10 plus 1 equals 0. Okay? Now, there's a couple ways to solve this. I first recommend it's typically best to have the leading term to be positive. So we could just multiply everything by negative 1. See, 4x squared minus 10x minus 1 equals 0. Okay? So we could think about using the quadratic formula here. Oh, it's correct. Okay. So let's start putting the numbers in. So we've got negative b, so that's negative of negative 10, plus or minus square root of, let's see, b squared is negative 10 squared minus 4 times a, which is 4, times c, which is negative 1, all over 2 times a, so 2 times 4. Okay, so negative of negative 10, I think, is 10. And we can split up this fraction with the plus and minus. That's just over 8, plus and minus, and all of this is over 8. And then what's 10 squared? 100. Okay, so this is going to be 100. And then we've got 2 negatives here. So it's 4 times 4 times 1 and 2 negatives. So I think that's plus 16, right?
Right.
All right, that's not too bad. 10 over 8, I think that simplifies. Let me go over here. We need the space. To 5 over 4. And then this is plus and minus the square root of 116 over 8, right? Now 116, let's think about what perfect squares are in that. I think it definitely has 4 in it. It does. And I don't think it has any other perfect squares in it. I think 116 divided by 16, which is a perfect square, is 7.25. Yeah, it's not going to work. So this would be 5 over 4 plus and minus the square root of 4 times the square root of 29, because 29 times 4 is 116 over 8. Now the square root of 4, we know this to be 2, so we can get this as 5 over 4 plus and minus, and then 2 over 8 simplifies to 1 over 4. Square root of 29 over 4. Now, by the way, we're not going to take the negative one of these. Now let's go back and make sure I understand why. The negative one of these would actually be over here. Do you see that? But that would be like for time before 0. So we're not going to worry about the negative one of these, right? So let's just say physically only take the later time, the positive, okay? So physically only take the later time, like the positive, okay? So we're just going to say x real, the real one, right, is going to be 5 plus the square root of 29 over 4. All right? So we should get that in our calculator. So let's type that in. So it's going to be, let's see, and make sure that's in parentheses upstairs. It's 5 plus the square root of 29 over 4. So it's about 2.5. You round it 2.60. You round it seconds. Yeah. Okay. Now I estimated. Remember I estimated earlier, a couple slides back. I estimated this is about 2.55. It was hard to say, but it turns out it's about 2.5. This is about 2.60. Okay, where it hits the ground. Okay, so right about there.
All right.
And that's right here. Okay, cool. All right, and I think we have just one more thing, and we want to do domain and range. All right, let's do that. So let's talk about the domain. And let's think about this. If we're just doing the flight of the ball, then the time should be x goes between 0 and what's the latest time it goes up to? What did we just solve for? Yeah, about 2.6, right? Okay. If you want to be really technical, I mean, you can use 5 plus square root of 29 over 4, but most people just write 2.60, right? And then lastly, the range is all the possible x values. Now, what's the smallest y value? What's the smallest height that the ball has? Down here.
4.
No, that's just its starting height. What's the smallest height it has over here? It hits the ground, so it's 0. But then the highest point is the vertex. And the vertex occurs, again, we already solved for that. The vertex occurs at, gosh, where did we solve that? 29, right? Right here, 1.25, 29. So we should go 0 to 29. Okay, that's the domain and range. Let's briefly review what we did, right? So we figured out that x was time. We wrote the table, and we looked at those points, right?
Right.
We started to sketch it, but then we sketched it a little better here. Okay, so we sketched it a little better here. We said that it should be like an ax squared plus bx plus c, and we said that a should be negative because it should be a downward facing parabola. It should be between 1 and 2 for the vertex, and then when x was 0, c was 4, because that was the starting height. We figured out what c was. But then we didn't have two variables. This is probably the hardest part. We didn't have a and b, but if we plug in 1 and we plug in 2, we get 2 equations and 2 unknowns, namely for a and b. So what we decided to do was solve for a and b. Solve for a and b via elimination, right? We used the elimination method. Okay, so using the elimination method, we just subtracted the equations. We got negative a was 16, so a was negative 16. And then you can go back to a plus b equals 24, and then you got negative 16 plus b is 24, so add 16, b is 40. So here's our function. And that's good because we could use the calculator, we could plot the function, and then we just drew horizontal lines at 20 and 28. We said the vertex indeed was above this point, and everything looked correct. Then we said, what's the function? We wrote it down. Find the coordinates of the vertex. So remember, that's the formula, negative b over 2a. We plugged the values in. We got negative 40 over negative 32, which is 1.25, 5/4 of a second. So that exactly corresponds to right here, which is halfway between 1 and 1.5. You can see that. That's the maximum height of the ball at 1.25 seconds. How long is it above 20 feet? Well, we know that at 2 seconds, it's at 20 feet. We just had to figure out what is this time. So this time right here is 0.5 comma 20. How do we do that? We set the function 20. Okay, so this here we set the function equal to 20. Vertex was part D, and then this was part D. This is part E. We wanted to find the earlier x where y equals 20. Okay, so we set y of x equal to 20. This, we subtracted the 20 over. We divided by negative 16. We knew that one of the times had to be x equal to 2. So we had to deduce the other one was x equal to a half. For part F, we wanted to find when it hits the ground.
Right.
So y equals 0 is when hits the ground.
Okay.
So we set the function equal to 0. We solved using the quadratic formula, right?
Right.
So then, once we solved, then we get the time when it hits the ground. This is the time at the ground. Remember, we threw out the -1 here because that would be a negative time. And then we said the domain is 0 to 2.60 seconds, and the range is 0 to 29 seconds. Or sorry, 0 to 29 feet. I mean, I wish it was easier, but that's how we do that problem. And that problem is very much an application, like a project in some sense.
Right.
Okay? And notice that, I mean, one of the things that this allowed us to do also is it allowed us to show how to use the calculator. So I showed you a couple steps in the calculator, okay? Because whenever you're doing application problems that like the numbers are like a little difficult, I would recommend use the calculator to try to confirm, right? And the calculator did definitely, because we found here that indeed this is what it should look like, right? That's a little more of a pristine. All right, good job. So hopefully now you've had a chance to see a really interesting application of order 2 polynomial functions. That is, x to the power 2 being the highest power, what we often call quadratics, and the shape on a graph is a parabola. And that particular type of application problem being applied to a football. By the way, this football would be in the absence of air resistance. It's not going to be a perfect parabola if there is going to be air resistance, but it turns out since the ball is not in the air very long, a parabola is going to be nearly the shape that this football has. So it's going to be a good approximation even in real air conditions, especially if there's no wind. And furthermore, hopefully you now see that if we have an order 2 polynomial, that if n is 2, then the number of points that we need p is 3. And the reason we need order 3 is because we need 3 parameters, namely a, b, and c. The coefficient in front of the x squared term, the coefficient in front of the x term, and the coefficient that's in front of the x to the 0 term, which is really just a constant. So we need a, the quadratic number in front of the x squared, we need the b, the linear number, and we need c, the constant term. So hopefully you now understand that you really need those 3 points, but you can predict everything about the ball's path. You can figure out how long it's in the air, you can figure out its exact trajectory and where it is at the various times, its highest point, when it strikes the ground, and so on. So I hope this is an interesting application problem. And let us know in the comments, how could you actually use this in your life? How could you use such a calculation to maybe have some points and then predict something's curve? So let us know in the comments about how you're going to use this. And I want to thank you for watching High Peak Education today. Please smash that like button if you enjoy this content. Please subscribe to the channel to grow the channel. Please share this video amongst your social networks. Links are in the description below, and I will see you in the next video.